name is Bryn, and I'm a mechanical engineer working mostly with heating, ventilation and air conditioning, energy using buildings. I work in a consultant company called Eriksson Horgen, and I also have a part-time professorship at the Technical University of Applied Science in Oslo. I'm going now to present the Opera House and the technical solutions there, and also I will present a new project which we just have finished the pre-design phase, and which also have quite a challenging situation with respect to the ventilation. That was the wrong way. We don't use it too long. Yes. So, it's important to find the right button. The Norwegian National Opera and Ballet was, the design started in 2000 and it was finished, the construction in 2008. So actually it has a 10-year celebration this year. The client is the governmental building agency, and the size of this opera house is 38,000 square meters, normal area, but if you include all the balconies and all these things, it's around 70 or 80 square meters. The design team, initially the opera was a competition and it was won by the well-known architect Snøhetta, which means a snow flute. And one might think that the design of the opera house is related to the name of the architects, but I think they have inspiration from nature when they do design. So the opera house has a metaphor is a metaphor for the landscape of the glacier. And in addition to Snøhetta, it was our company, Eriksson Horgen, and it was Per Rasmussen that was electrical, and it was Bryn that was a construction designers. The different areas is it has 3 stages, and it has orchestra rehearsal and ballet rehearsal, and they also have workshops for tailors and carpenters, and of course offices and restaurants. So I think it's 700 people working in this opera house. So this is from the main theater. The design was very much focused on the acoustics. So what you see here, the balconies, the shape of these balconies are designed according to the acoustic design. It's made of oak, and it was produced by a shipbuilder because they were the only ones that were able to produce such advanced woodworks. And this is the Black Box Theater. It's a more simple room, but it's here you can reconstruct it and have seats in the middle or seats around, so it's more flexible theater. This is from the ballet rehearsal. Here they have very good light, and they are also here been working the acoustics, as you can see with the walls. This is from the painter workshop. Also here they had a great focus on light and daylight. As you can see, it's a window up into the roof. And here it has been a lot of work with getting good ventilation solutions to avoid damage to the health of the workers. Just very strict and strong requirements for this building. Of course, it was Oh, it's not, I have a, okay, it's 17 decibel A. For the ventilation system was a #1 requirement. It was the sound and the acoustics was the main focus for this building. So it should be maximum 17 decibel A in this main theater, which laid the basis for all the duct work, all the work with the ventilation system. So, and we have the backstage and the main stage and the orchestra pit and the main theater. So it's 4 areas that is connected, and we want to fulfill the requirements in all these areas. In the main theater, it's designed for 1,350 persons. In the orchestra pit, it's 80, and on the main stage, we don't know how many. It can be in there, hundreds of people. So it's a very high load from people in this main theater. And this is what you see. This picture is actually a model that was built for the acoustics. So they did also physical testing. The solution was that for the ventilation is that it is displacement ventilation here in the main theater and in the orchestra pit, and on the stage it's a mixed ventilation. It was not possible to have the displacement ventilation at the stage because there is so much of the stage is possible to move up and down, and it's a very, very wide area. I think it's 8 or 9 times what we here see is the whole stage, because they are able to move things in and out. The requirement for the temperatures and the humidity we can see here. And as you see, the minimum temperature is 20 degrees and the maximum is 26. And what was put up was a different requirement for different areas. And for the main stage, it should be 45, and in the backstage and main theater, it's 30 and 35. And this has been really a challenge. I'm not sure if it's possible to have a different humidity because the air mix so easily. So I'll get a bit more into this and tell you a bit more about this. Here we can see the principles of the ventilation systems. Down here is a ventilation system for the main stage, and it has supply at different levels. Here is at the lower level, and this is on the balcony level. So they can have a lower temperature at on the balcony. And it's one exhaust up in the top. And here's a separate supplier unit for the orchestra pit. They get the supplier on the floor. And up in the left is a system that supply air to the stage. And here you see the supplier to the stage is divided into one area for the stage and one area for the warm-up for the singers. So they can have different humidity in these areas. And all these systems should work together. And of course they have rotary heat exchangers, and they have humidification, all of the systems. Very much because of the sound or the acoustics requirements, we had a lot of focus on the air velocity, and so we ended up with an SFP on these systems around 1. So it's a very, very good with respect to energy efficiency, also these systems. So that was it was designed as early in 2004, and then people thought we were crazy when we talked about SFP on 1, but now it's not crazy anymore. So it's interesting to see the development. It's the supplier units, the supply air units, and very much of the ventilation system was supplied by Swegon, and that is also maybe one of the reasons they are here. The supplier units, they should be supplied under the steps under the seats in the theater, and this is a very normal solution with the plenum below. What was not that normal is that when this was built, it was not built as it was drawn. So we ended up with it was a lot of woodwork that was used that we did not expect and that we did not see on the drawings. Maybe this would have been better today with a BIM, maybe it would have been more correctly. So we ended up with these openings. They were 2 or 3 centimeters lower than in the design. So in this area where sound and climate had the main focus, it was a terrible situation. I remember it was around Easter in 2005 we discovered this, and it was really a stressful situation because we had to redesign. And luckily Swegon and the Building Research Institute in Norway, and also the acoustic engineer, they engaged very much in this. So we had a very good solution. Yes, and here you can also see below the stage, no, not the stage, but below the seats. So you also see we had a very reduced openings, but it was also filled up with a lot of electric items and sprinkler. That was not the sprinkler was shown, but not all the detail on the electricity was not shown. So this was also a challenge because the air should move out without any noise. So we had to redesign, as I told you, and the first units we got showed that it was too much false noise, and the comfort criteria was also a problem. And then the designers collaborated, and we tested the prototypes. And it was made tests during night to have it completely quiet and to test the sounds. And it also tested the air velocity and the temperature in distance. Here are the supply, and this is 34 centimeter, 47 and so until 84, and in different height. So we there measured what you see here. We measured the velocity, the standard deviation of the velocity, the turbulence intensity, and the draught rate. And we had, I think, 3 or 4 different solutions, and ended up with one that was good for the reduced area. So that was a very happy ending of a very stressful situation. So this is another picture from the main theater, and here we see this is what you see. This is a very hard use of this room. So here they had some problems with they had to follow up it and to check that these things are not moved or fallen out. Here we have also the supply units in the floor. It was not, because it was reduced area, we had to put some extra supply with these other units. The climate situation in this theater is good. Here we see some measurements from the evening with the full full public, not full audience. Here you see the supply temperature is around 18 degrees, and the temperature here on the backstage maximum up to 24 degrees. And in the main theater, it is kept. It is here. It's around 19 to 20 degrees. And here we see the humidity, and this shows one of the challenges. The pink one is from the orchestra pit, and here we see that there's fluctuations in the humidity, and it is especially in the orchestra pit. It shouldn't be like that because of the instruments. But these guys, they are running the building, and Erik has been there since before it was finished, and they are very happy with the solution in general. They have very little complaint except for the humidity, but the audience is very satisfied, and the temperatures are well within the limits. So that's I think that's a good, successful solution. Yes, as I said, it is challenges with the orchestra bit, and there have been studies working on this with measurements and the smoke, putting smoke and measurements of humidity and temperatures. So we have been trying to find out, and here we can see from one test period that we see that the temperature is quite stable, but the humidity fluctuates between below 30 and up to 40%. While in the main theater, it's quite a stable situation. So we have come to that it's likely that these fluctuations is the reason is that it's doors that is open around the entrance into the orchestra pit, and it is also openings behind the stage that make drier air coming in. So what they now are doing is that they put the same humidity on all air, both in the orchestra pit and also in the main theater and the stage. So this has led to, of course, higher energy use because it's a higher humidity than originally was planned. So this is something one should bring further to other projects, that it's hard in one building to have different humidity zones. And then I will move over to the foyer. It is an area where the architect had a lot of wishes for how this should be. And of course, like always, they wanted to be open and transparent. And this is the foyer is a very important part of the architecture. So it's a huge glazed area. To the south, it is 570 square meters. You can imagine, if you think that it's 1,000 watts coming into 1 square meter, it's 570 kilowatts solar energy in this, when it's directed to the south, so it's quite extreme. And in addition, it will be a high number of persons being there. And the guesstimate was 700 people when the solar gain is at the highest. And they also wanted this open balcony, as you see here, towards glazing. So then we have to have a strategy for how to solve it. And of course we wanted to have as simple solution as possible, and as using as little energy as possible. So we focused very much on the solar protection of the glazing and also having solar protection behind the shading behind the glazing. This was tested so that we were sure that it was good enough solution. It was tested at the Bryn University. And we had a displacement ventilation supplying air from behind the balconies and behind the artworks. And with the exhaust behind the shading in the top of the ceiling. We also had solar cells on the south facades suggested. That was also something at that time when we suggested this. It was said to be ridiculous. But it's also interesting to see how it changed. Now it's something that should be in every environmental friendly project. So it has been an interesting development. And then finally, our plan was that we would make acceptable climate down here and accepting a higher temperature up there and just putting cooling at the balconies. So we made simulations, we made a two-zone model and made the simulation so that we would have maximum around 25 degrees. This is the air temperature and this is the operative temperature in the foyer, and letting the temperature up in the upper part be what it would be. So we accepted up to 40 degrees. So this is a solution with the glazing, and you can see the shading. Here you also see these shelves, and these shelves are there as a part of the winter design. So this is the next. So what they say, these guys that I showed you, they say that this foyer is a place where people come when it's too hot outside. They come in here to just feel that it's cool and it's nice to sit down. And as I said, the air inlet was partly behind the art, and this is the art. It's an art pretending it's symbolizing the ice glacier being pressed together, and so it's opening behind here, and the air comes in from there. I also was happy to be there on a party with 1,500 people, and because it has been one of the best party places for big companies that sponsor the opera. And it was outside, it was 26 degrees, and it still worked. It was really nice to be there. Here you can also see this solar cells shading. These shadings are a bit outside, so we have an outdoor terrace there that is also shaded by these solar cells. And here you can also see, up there you see the shelves, and you see that there is no heaters up there. So this is how we try to do the design as passive as possible, even though it's not fully passive, but we try to avoid a lot of technical installations. So this leads us to the winter situation. The windows, they have a U value on 1.2, so it's not the best. Today we would have chosen better, I think. I'm sure. Not only think, I'm sure. And here we have as I told you, we have these spoilers or shelves up under the windows, and we have floor heating, and there's a few radiators along the facade at the south side, but nothing around here up in these big facades. But still, people are very satisfied and happy with the situation, even though there's not any heavy heaters in this room. So this means that these shelves, they work and stop the draft from the window. And one other good thing is that we avoid having warm air passing the window and increase the heat loss. So it's also a very good energy efficiency in having this solution. And the next picture shows this here. I think I like this picture very much because what you see is that the snow stays on the window. And that means that the window is cold, and that means that it's not heated up. So even though it's not very often this happens, but in a way it's a proof that this is a rather energy efficient solution, because otherwise the snow would melt directly and just fall down. I think it's only me that see this in this picture. And here, this is a picture of the solar cell facades. It's 350 square meter. This was it's integrated into the glass. So this was a production made very early. It was, I think it was produced around 2005, 2006 or something. So it was a very early stage of the development of these solutions. So if we should make this again, I would, for example, suggest that one should have some extra glass, because it's when you make such special design, it's if you have a breakage, it's hard to get a new one that is exactly the same. So this is one of the things we have seen working with such special projects. You should always make some spare parts to get it similar. I think we did it with supplier units. There we had several spare parts. And over here you can see the little room that is not a balcony but an outside eating area. It gets very, very hot there. Because you have the white marble and the sea that reflects the sun. So actually the solar cells have produced more than calculated. That's, I think it's because of the effect of all the reflections. It's very bright. So this was a short presentation from the Opera House. Now I will like to move over to the new Life Science building in Oslo. It's a UiO, is a University of Oslo. And this is this project is really one of their strategic ways of moving. Because earlier at the university we had a tradition of having a faculty of biology, of chemistry and pharmacy separated, but now they are going to put it all together into life science and start to work together. So that is a change for the university, and they have to think in a new way. So actually they have already established the Life Science Center, but they don't have any building. So this is a building to be built. And here it will be both education and research. The area is 65,000 square meters. So here is it was a competition, and we were lucky and were part of the team that won. And the first picture was from the proposal that won, and here is a bit later picture when it has been ripening and developed a bit further. So it will have a lot of student areas in the first floor, and in the front here towards the south it's offices, and in the back part of the building it's a lot of laboratories, heavy laboratories. And they also have a lot of microscopes and NMRs and equipment that is very sensitive and that has very high energy use, high electricity power use. As I said, the pre-design was finished a year ago, and now we were lucky this autumn that it has come on budget to further development in the spring. So the detailed design will start in the spring. Yes, and this is a first project that the Statsbygg decided to have Bryn certification. Initially, they just wanted to have environment targets, but then they decided, because the university wanted to have a Bryn, they wanted to be more ambitious, and then Statsbygg said, okay. So they accepted to have a Bryn certification, and they wanted excellent, and that is quite ambitious. So that was a target we had to work along with, and which was very interesting. So the main target for the users was to get a flexible building, a building that they could change. Because that was a big problem where they come from, that everything was fixed and they had bad working conditions, especially in the laboratories. And they wanted, the university wanted to bring excellent. At Statsbygg, they wanted a near zero energy buildings. They kept their own targets during this phase. And the project is called Bryn, and that means live, as things going like this. And that was because the architect has tried to make a view of their design. Yes, and now I'm going to tell a little about the climatization and the energy concept of this building. What is special is, of course, the building and the use, and the ventilation demand is quite extreme. The power demand from the user equipment is also very extreme, and this can lead to extreme power demand for heating and cooling, because we have some data on this user equipment, and if you use standard information about the power use of this equipment added together and add that with all the ventilation, we'll get extremely high power for the central units. And we were afraid that this could be too high, and what we experience is also from building owners is that the central components very often are too high and too big, and then very seldom go on more than 50% capacity on the cooling and heating side. So we focused on trying to go into this, and also we studied the nominal and the expected energy use in this building. So the typical activities here is that the research in the laboratories, and we also have the teaching of the students. And they have both heavy computers, which is more and more taking over in science, and they also have all this heavy laboratory technology they use. And in addition, they are going to have laboratory activities for both bachelor, master, and PhD students. So this is quite. So this is just a few pictures from the pre-design. This is design in BIM, which we used from the very beginning. And this is from the low floor. Here we have a separate area to move the pipes and the technical solutions. Here you see a plan, and it looks more like inside of a body, I think. You can see that, and it has been a very successful project because the architect understands that this is necessary. We need this ventilation. We need to focus on this to get a good result. So therefore, it has been a very good project, developing good ways of handling this. And so here, this is a typical section. From the front part is the office part, and the back side is a laboratory side. And here you can see the roof. We will also see that this is a very technical roof with all the technical rooms for the supply air units popping up there, and it's also ductworks moving and the exhaust air coming up here. So, but as the roof is also a facade that can be visible, there's been a lot of work together also here with the architect to get good solutions. So we have been working on this Bryn, and we actually got the first certificate. We managed to get it, and I will tell you a little bit of the way to find to fulfill the energy part of it. Because the target for the energy efficiency was to get 10 scores, and that means the reduction of the energy use on 55% compared to the building regulation standard. So that is quite high reduction. So our strategy here then was, of course, work on the passive house principles, but also working on energy efficient ventilation, low temperature heating and high temperature cooling, reuse of energy from cooling and energy storage, and solar cells on the roof and facade. Actually, in the beginning, our plan was to have boreholes to heat the buildings, but when we have gone through the whole process and see how much internal heat we got from all the equipment, we found it was wrong to have this boreholes, and it was better to rather use this heat to reuse the heat. That was a better principle. But one challenge has been that when we are working for this Bryn documentation, you are working on a standardized way of simulating, and it's a standard university which doesn't have very high ventilation. But our university has extremely high ventilation rate, so we have to work in parallel both with the reality and with a standardized way of calculating. So the theory and the reality was not exactly the same. It was, as I have told, lots of laboratories with this very demanding, energy-demanding equipment, and a lot of the areas have 24-hour ventilation rates, and it's a lot of exhaust that is going all the 24 hours. And we have a risk of contamination of the supplier if we use rotary heat exchangers, and we also have this extreme variation in the ventilation mode. And this is shown here. In the very beginning, we tried to find out what are they doing in other countries, and we found this study from the University of California, and they show here that in the typical lab the flow profile is from 8 up to 48 cubic meter per hour and square meter. And this is quite shockingly high, going up to 48. And it's a challenge to find out what are you going to design both the local and the central units for. If you calculate all units for 48 and add this, you get 2 big central units. So we also find some studies from the UK. A very interesting one. There they had documented the energy use per unit area for similar buildings as we are going into. It's a Cambridge Chemistry Building, Edinburgh Cancer Research Centre, and buildings like this. And what you see here, it's quite interesting high figures of energy. They are I think the lowest is 652 and the highest is 979 kilowatt hours per square meters. And that is quite extremely high, and it's about 10 times the target of this building in the nominal values. So, but I think it was interesting to have this as a background to explain for the customers that they could not expect the standard values, but they could expect something better than this. So we were working towards that. And here they also explain that it's the ventilation that is the main challenge and the main reason for the high energy use. So the ventilation here at this project is a bit above 1 million cubic meter per hour that is treated in this building. And the solutions here, again, we have been focusing on having a low SFP, and also demand control is very important. And we wanted of course, in the areas where it's possible, we have a rotary heat exchanger, but we wanted to have as much high ventilation efficiency as possible. So we are here looking for a solution with that has a high recovery system. So, Swegon, if you can find something for us here. We are interested in discussing this. Because in the laboratories, the air will flow 24 hours all year. This is the final design as it is now on the central energy supply unit. That we have here, we have the heat pump that is part of the system, and here is a delivering cooling system, local process, low temperature and low ventilation, and here is the storage volumes for the cooling part. And here on the heating side, we have a storage volume for the heating, and we have snow melting, and we also have some extra supply from the district heating. And it's also chillers on the roof if you can't get rid of all the energy. So this is the solution as it was changed actually in the very end of the pre-design phase, when they realized that we had such an enormous amount of heating from the cooling system. And in addition, there's solar cells on the roof, and that is made because of the energy targets. So it's solar cells both on the roof and on the facades. We are now maybe going to try to avoid it on the facades and only have it in the roof, because it's a much simpler solution. So with this strategy, we are now in the theoretical standard calculation, we are down on 71.2 kilowatt hours per square meter. But we know it won't be that. And we have been very focusing on, excuse me, telling the customer that it won't be that, because you don't have a history faculty, you have a laboratory faculty. And these values are standardized for universities, which can be anything from history to laboratory. So, and the solar energy produces 12.3 kilowatt hours per square meter. And so we started to go into and studying more into detail the real use of these buildings. And for example, we had a look at the capacity of ventilation. If we took a total simultaneous capacity on 60%, 40, 60 or 80%, you can see the change in the maximum power for cooling and heating. It's extremely big variation. And you can imagine a power plant on, for heating, for example, on 3.9 or 3 megawatts, it costs a lot. And it's not, it doesn't only cost for the heat, the power plant itself, but it's also the pipes and it's electricity, and it is flowing all the way. So it's a huge potential to optimize this, both by finding the right simultaneity and doing the right design. So this has actually been a design process that we have been allowed to work on after the pre-design was finished, just to optimize this, because we discovered this potential very late. And the reason that we got it so late was that it was a hard work to get all the information from the users. So therefore we worked on this this project to study simultaneity, both for the ventilation and for the equipment. And we saw that you had one situation on the Bryn level, another on the floor, and on the plant, and also for the whole building. And we're trying to put this together to make accumulating values to avoid having 100% up there in the top. So they made studies of the fume hoods, and investigating how they were used and how many hours they were used by the laboratory people. We made queries by the people that was going to move into these buildings. And as you see, it's very important that they are structured and they close their fume hoods when they don't use it, because when it's closed, the exhaust air is 200, but while it's open, it might be up to 1200. So the use of fume hoods is very critical. We also had a dialogue with the university people about how they were going to use it, because they have classrooms. And in the classrooms, they might teach 25 students at a time. And so the university actually they went into their time schedule. And so we put this as a basis to see how much we could expect to have a simultaneity. And so we see that actually we are coming quite high. I think we wished that we could have come lower than up to, I think we ended up with around 70%. So it's quite high on this. But this is only for the fume hoods. So now, actually this spring, we have got a master student that is going to continue work on this. And he will go into study research labs for 6 persons and educational lab for 25 students, and look at what we call the Danish and Norwegian solutions, and look at the different supplier units, control strategy, location of fume hoods, and growth situation. So they're also Swegon, if you have some to give us some input, we are interested in this, because this will be probably a full-scale testing and also CFD modeling. So this was a work with ventilation, and then we in parallel did some measuring of the lab equipment, and it's you can't imagine all the equipment. Some of it is self-made and some of it is new, and they are going to bring it all because they don't have the money to buy it all new. So both the mechanical engineers and the electrical engineers was very interested in getting data on this. What is the real load? What are they really using of energy and how long? Because on the things that you buy, you might have a number on the back side, but maybe it's not running for a very long time. So we chose, we went through all the equipment, and it's thousands of them, and we decided to select, have to make a selection, and we chose those that had a few of those that had very high load, and also those that it was very manual, so that we should get a good picture of the situation. And also those that were running for a long time. And so here you can see a typical picture of what this is. This is results from a measurement from a dryer, and as you see, it has a very, very high peak. But and which was the number? It's a top figure, and it's a top figure there that you can read on the back side of the equipment. But as you see, the base is much lower. So we used this data and made a basis for use in the simulations of the energy use and also for the design of the central cooling units. Because with this data we could take a risk to reduce the load to a more reasonable level. And so we made an overview like this. So here, this is in Norwegian, but this is the grey one is the base load to the fan coil, and the green one is the unit that is directly cooled, and this the three on the bottom is variating fan coils, and the top is the variation in the direct cooling. So we got a reduction in the load from this, and then in addition we added the storage that also could reduce the load, because you have a very high load during the day and lower during the night. And we wanted to have storage units like this. I think it's a Swedish project that is shown here. And it's also used at the other universities. And we had a building model. We were simulating this building in either ice, and we combined the results from either ice with the measured data on all this that is cooled directly into a huge spreadsheet itself. And so we got this load profile. This is every hour during the year. And here you can see that this is a heat pump, the red. And this, the yellow, that is district heating that you see in winter. We need some extra. And this here is a process cooling. This is a blue-brown band. And this shows why we decided we don't need anything other than this, because it's so huge amount. And this darker blue is ventilation and not for cooling. So this is for the ventilation and it's hot outside. So with this as a base, we could calculate more expected real energy use. And here we also do some variation studies, so we ended up with an expected lower level energy use on 255 kilowatt hours per year, and a high expected 360. So, and still having a Bryn excellent building. So this is how we are now. One thing that we are questioning ourselves is that what happens if this light blue one is reduced, that the use is completely changed. Then we have a challenge. So we have to discuss this, maybe we should have some more holes just in case that this will be changed. Yes. This was the end of my presentation. Thank you.